Okay, very good. So, okay, I'm sorry, this problem is definitely given to us as twisted as possible, and you know that, so I'm going to write this. And then, of course, I'm going to factor out x, and I'm going to factor x minus 1 and x minus 4. Do not rush, do not touch this, do not try to simplify, don't try to do anything. We have to get our table going with f prime, f of x, and the second derivative. Obviously, I see that 1 and 4 are a problem. Only now I can simplify, and I get this. The factor that disappeared must be a hole in the graph. So x equals 1, a hole. The factor that stays must be a vertical asymptote. At this point, I'm trying to exhaust the function. I'm trying to find everything about the function that I can possibly determine, and then move on to the first derivative and second derivative. Okay, so first I'm going to plug in 0. 0 over negative 4 is definitely 0. I need to find what happens here, 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 and here. So I'm going to start with the end behavior and find limit of negative x over x minus 4 as x approaches negative infinity. I'll say, okay, it's infinity over infinity. I know how to address this now. The numerator prime is negative 1 with this negative, and the denominator is 1. So then the answer is negative 1. Which means y equals negative 1 is a horizontal asymptote. I don't need to determine the other one because this is a pure rational function. So negative 1, y equals negative 1 horizontal asymptote, y equals negative 1 horizontal asymptote. Okay, now I have to determine these limits here with left of 1. So limit as x approaches 1 from the left of negative x over x minus 4. Then I need limit as x approaches negative 1 from the right of negative x over x minus 4. And then these two. So limit as x approaches 4 from the left from negative x over x minus 4. And the last one, limit as x approaches 4 from the right of negative x over x minus 4. Okay. So here there's no problem when I plug in 1. The numerator is negative 1 and the denominator is negative 3. So it's 1/3. The same thing has to happen on the other side. This is positive 1. Sorry, we're at 1. So I plug in 1, negative 1 at the top, and 1 minus 4 is negative 3, 1/3, of course. So this is the whole. So the whole is 1 comma 1/3 when I get to graph it. I know that these must be infinities, no question there. So 4 from the left is a negative number at the top, but 0 in the denominator, but 4 from the left will be 3.9. So this is also negative, so this is positive. 4 from the right, still negative at the top, but positive in the denominator, so that's why x equals 4 is a VA. This is what we did a long time ago. In chapter 2, I believe. Okay, so I have positive to the left, oops, positive on the left hand side and negative on the right hand side. Okay, I'm done here. Nothing can be done, I cannot discover anything about the function from the function itself. I'm ready to study the first derivative. So f prime of x, leave the negative outside. Top prime is 1 times the denominator minus the top times the denominator prime, which is 1 over x minus 4 squared. In the next step, these two will go away. The negative 4 becomes positive 4, and I love it. I don't have to do anything. It's always positive. It's undefined at 4, but so is the function, so it doesn't mean anything. No critical numbers ever. So now, I try to make sure, I'm checking whether these two are working well. If they're not, I'll say oops, and go back to the drawing board. From negative 1 to 0, it's going up, yes. From 0 to 1/3, it's going up. From 1/3 to infinity, it's going up. From negative 1 to negative 1, it's going up. It looks fine. Good. Now I will study the second derivative. Where is my first? Here it is. Here's my first derivative. But of course, I'm not going to use this when I differentiate. I'm going to use this. And that reminds me, one of you changed the square root into something like this, but the square root of x does not equal x to negative 1/2, but x to positive 1/2. So please be careful with that. I just remembered when I graded it this morning. Okay, so I'm differentiating, bringing negative 2, sorry, careful. It's 4. I talk about negatives and I messed my own up. So it's 4, and x minus 4 to negative 2. So I have negative 8, x minus 4 to negative 3 times the inner function prime, which is 1, negative 8 over x minus 4 to the third. For the purpose of the studying of the sign, it's never 0. Please use this for simplicity, because there is no point in plugging anything in here. It's all positive. This piece is all positive. So don't worry about it. Just worry about these two. So, to the left-hand side of 4, when I plug in, let's say 0, 0 minus 4 is negative, with negative in front is positive. To the left-hand side of 4, everything is positive. So the function holds water, we say. On the other side of 4, like with 4.1 or above, I get positive, but this is a negative sign. So, and this is it. No symmetry, no inflection points, no max min. The function is always increasing, but opening up and opening down. It has a point of intersection of x and y at the origin, and it has a hole in the graph. Two asymptotes, x equals 4 and y equals negative 1. And now that's all I need, just the table. The rest doesn't mean anything anymore. One, two, three, 4. Negative 1. And now I'm ready to graph. I will start with 1, comma 1/3. Oops, I don't want this color. I want this color. 1, comma 1/3, and also this. So coming from approaching negative 1, crossing the x and y axis at the origin, going through this hole, you know what I mean, and then going up to infinity. On the other side, opening up, increasing and opening up. The other side opening down and increasing all the time from negative infinity to negative 1. And I think we have 4 minus 5x plus x squared. Yes. Any questions on this problem? Anything? So this was problem 3 in 4.5. Let's see what else is there. Anything else from curve sketching? So we're looking at this, and we looked at this, and we looked at an example like this. Oh, what I forgot here, I'm sorry, we have to insert, I'm going to say 2.5. 2.5 is Rolle's plus the mean value theorem. I forgot, I just remembered. Okay. Anything else? So I guess we know it all chapter 4. We don't have anything else to look at.
Maybe going back to like an example or two from Rolle's and mean value theorem.
Very good.
Just
Very good.
Our memory.
Perfect. So I'm looking at the web assigned so I can help you with that. So that is section 4.2. I clicked on the wrong section, sorry. So it's still section 4.2, I just clicked on the wrong. Okay, view. Okay, so let's take a look at that. Very good. So I'm looking at problem 2 in WebAssign. Verify that the function satisfies the 3 hypotheses of Rolle's theorem on a given interval. And then find all numbers C that satisfy the conclusion. So we are given a function that is 3 minus 8x plus 2x squared, and the interval given to us is 1, 3. Okay, so in number 1, if you remember, we have to show that the function is continuous on the 1, 3. It is. It's a polynomial function. In step number 2, I have to say that it's differentiable on at least the open interval 1, 3. Of course it is, for the same reason. The polynomial function is continuous and differentiable everywhere. In step number 3, I have to find f of 1 and f of 3. If they happen to be equal, then Rolle's theorem is applicable. If these two are not equal, Rolle's theorem is not applicable. So I have, what is it? 1 minus 8 is negative 5. Negative 5 plus 2, I got negative 3. 3 minus 24 and plus 2 times 9, which is 18, I got negative 3. So because 1, 2, and 3, Rolle's theorem is applicable, therefore we say by Rolle's theorem, there exists a C in the open interval, in this case 1, 3, such that f prime of c is 0. In other words, there is a term, there is a max or a min somewhere there. Okay, then so we find the derivative, which is in the correct order 4x minus 8. And now we create this equation as 4c minus 8 equals 0. And from here c equals 2. And it better be in the interval 1 comma 3 because it's guaranteed by Rolle's theorem. And that was it.
Thank you.
Perfect. Is this clear?
Yes.
Okay, so now for the mean value theorem. Remember, you can find more than one c, but at least one, guaranteed. So let's look at, I see your question number 4 in WebAssign. We have f of x, 3x squared minus 2x plus 1. I'm hoping that when you start working on these sections, then by Wednesday you're going to come back with more questions, and by next Monday with more questions. That's my hope. Does it make sense?
Yes.
Okay, so now we're talking about something else. So in part A or part 1, I'm going to say the same thing. It's continuous on the interval 0, 2 as a poly. I also say that it's differentiable, at least on the open interval. It doesn't have to be differentiable at the endpoints, but at least inside the interval, but except potentially at those points, for the same reason as a poly. Now, there is no third hypothesis here. Immediately we go to, by the mean value theorem, there exists a c in the open interval 0, 2, but now f prime of c equals f of 2 minus f of 0 over 2 minus 0. The rate of change is the same with the rate of change between those 2 points A and B. Okay, so now I have to find c that satisfies this condition. So I have to find f of 2. So f of 2 will equal 4 times 3 is 12 minus 4 plus 1. I have to be careful because Sean is watching me like a hawk. So 13 minus 4 I think is 9. And then f of 0 is 1. I'm kidding. You should. Please do. Okay, then f prime of x is 6x minus 2. And of course, f prime of c will be 6c minus 2. And now I build this equation. The left-hand side is this. So 6c minus 2. And the right-hand side is 9 minus 1 over 2 minus 0. So 6c minus 2 equals 8 over 2, which is 4. So very nice. 6c equals 6, so c equals 1. It's guaranteed to be in the open interval 0, 2. Guaranteed by the mean value theorem. Okay, I'm looking at the other problems. Yes, so let's do a problem either 7 or 8. Can you look in WebAssign in 4.2? See whether you want 7 or 8. I want to help you move forward or more faster into this.
8 looks interesting. I don't know if your 8 is the same as mine. But
Is the one with the f prime greater than or equal to 3? F of 3 equals 1.
Yes. Yeah. Mine's a little bit different, but yeah.
Okay. So let's look at number 8. So I have f of 3 equals 1, and f prime of x is greater than or equal to 3 for all x in 3 less than or equal to x less than or equal to 7. Okay, so it's asking now how small can f of 7 possibly be. Good, we haven't seen anything similar to this before. Good pick. Okay, so what we know from here is that we are discussing an interval between 3 and 7. This is what I know so far. If I'm looking at the interval 3, 7, where the derivative is a number greater than 3, it exists. Otherwise, it would not be a number greater than 3 or equal to 3. So the derivative exists. So f prime is greater than or equal to 3 for all this interval. And because I have an interval where I know the function is differentiable, it must be continuous. Otherwise, it would not be differentiable if it's not continuous between 3 and 7. I know that from here I can write that c exists between 3 and 7 such that f prime of c equals f of 7 minus f of 3 divided by 7 minus 3. For any function, let's stop for a moment. For any function that is continuous and differentiable on a particular interval, I can always write this for that interval. And that's what I did. So I'm told that this function is differentiable. Once I'm told that the derivative is greater than 3 and the function is differentiable, it must be continuous for all x between these two in this interval. So therefore, I have an interval where the function is differentiable. I don't care for this just now. So on this interval, the function is differentiable. It must be continuous. So by MVT, there is a constant c, a number c, between 3 and 7, and I can write this. Okay. But I'm told that f prime is greater than or equal to 3 for any c between 3 and 7, which means all this f of 7 minus f of 3 divided by 4 must be greater than or equal to 3. 13, 14, 15. Okay, that is given to us, it's known. Okay, I am given that f of 3 is 1. So then f of 7 minus 1 over 4 greater than or equal to 3. Obviously, I will multiply both sides by 4 and move 1. See how many interesting applications of the mean value theorem? So, how small, given the information we have, how small can f of 7 possibly be?